Yes, guys. Tell me last class what you have studied. Just unbalanced three-phase systems. In that, we seen a
Star
basic about
connection, delta connection.
yes, a star connected load and delta connection load. How the phase current, line currents are related in star, and phase voltage and line voltages are related in delta. Tell me, in star connection, phase current and line current is
Equals
equal. In delta connected,
voltage, phase voltage and line voltage will be
line voltages are equal. Okay, and we seen the types of load in that. Here, I will just do this one. We seen this one for unbalanced load. IR is equals to phi phase divided by Z1 angle of minus pi 1 ampere. Then second IY equals to phi phase Z2 an angle of minus 120 degree minus pi 2 ampere. Then IB is equals to phi BN, that is nothing but phi phase by Z3 angle of plus 120 degree minus a pi 3 ampere. Okay, here this is the case for unbalanced load. Okay, here I can say Z1, Z2, Z3. Sorry, Z2, here Z3. This one is with an angle of pi 1, this one with angle of pi 2, this one with an angle of pi 3. Okay, then the current flowing through this phase is, that is V phase divided by Z1 at an angle of minus pi 1. Then if see here RYB is my phase sequence. So IR minus pi 1, IY minus 120 minus pi 2 plus 120 minus pi 3. Okay, now today we will just see how we are going to analyze the three-phase unbalanced loads. Before that, I will tell what types of unbalanced loads are there in our three-phase system. Okay, first one, see here, I can say unbalanced three-wire star connected load. Unbalanced net first one, unbalanced three-wire star connected load. Okay, second one, unbalanced four-wire star connected load. Okay, again in this unbalanced four-wire star connected load, we have neutral wire with zero impedance, neutral wire with zero impedance, then neutral wire with impedance, neutral wire with impedance Zn. Okay, then coming to third one, that is unbalanced delta connected load. Balanced delta connected load. Okay, these are the types of unbalanced load, where first one, unbalanced 3-wire star connected load. Here we are missing neutral wire. Okay, it means it will be like this. First one, if I'm going to say this is star connected load Z1, Z2, Z3. Okay, for this star connected load, we don't have any neutral wire. Neutral wire is missing for this. Star unbalanced 4-wire star connected load, that is 4-wire in the sense here this is my neutral point. Okay, R, Y, B, N. We know this N is neutral of supply. This one I can mark it as O. Generally in all the textbooks they are going to mark this neutral wire as O, this as N. This is unbalanced 4-wire star connected load, where we are having unbalanced in the sense pi 1, pi 2, pi 3. Neutral wire with zero impedance, where I can get I N equals to IR plus IY plus IB. Neutral wire with impedance Zn, the currents are different, as well as there will be a voltage difference with O. Then unbalanced load, simple, pi 1, Z2, pi 2, Z3, pi 3. Okay, now how we are going to solve this one, how we are going to analyze this one? There are two methods. First one, application of Millman's theorem. First method, application of Millman's. Second one, mesh or loop current method. Measure loop current method. Application of Millman's method or measure loop current method. We are going to analyze unbalanced, that may be star or delta connected system. We are going to solve the problems according to Millman's theorem or measure loop analysis. Okay, we'll first see the theory behind these two methods. We already know Millman's theorem. Tell me, Millman's theorem, what it states?
So if there are n voltage sources with internal resistance connected in parallel, then these voltage sources can be replaced by a single voltage source.
Yes, correct. Millman's theorem. It is possible to combine number of voltage source or current source into a single equivalent voltage using Millman's theorem. How? We all the formula for that as Vm is equals to summation of K1 to N Vk yk divided by summation of 1 to n yk. Okay, then Zm equals to 1 by summation of k to 1 to n yk. This is the formula. How we are going to use here in the sense, for this I am going to refer this figure. Let us consider star connected load. Star connected load, this point is neutral, ZA, ZB and ZC. This point A, point B, point C. Okay. Supply A, supply B, B, C, A, B, C. Okay, this is my, what type of load is this? First load. What is that? 3-wire star connected load. Here neutral wire is not there. Okay, now I'm going to apply Millman's theorem for this. Okay, now phi n naught vector phi a naught, then ya vb naught vc naught yc divided by ya yb yc. Okay, I already told what is O represent. What does this O represent? Yes, N we know, neutral point. O is neutral point of this star connected load. Supply. Okay, here VA naught, VB naught, VC naught are the voltages VA naught, VB naught, VC naught with respect to the supply neutral, that is the phase voltages VA naught, VB naught and VC naught are phase voltages. Okay, we are writing with respect to neutral of the star connected load with respect to the neutral of the supply O. This is V in naught. Okay, here YA, YB, YC are the admittances that we know. The reciprocal of admittance will be given as 1 divided by J ABC. Okay, now see this figure. I can write voltage 2 the phase this phase to phi A phase to neutral point phi an equals to tell me. That is nothing but the phase voltages. We are writing the voltages with respect to the neutral of the star connected load. Okay, here phi A naught is the phase voltage with respect to the supply neutral. Now I can easily write phi an is equals to phi A naught, this phi A naught plus phi ON. This phi ON is nothing but the voltage difference between neutral of star connected load and the neutral of supply voltage. Okay, if I am going to connect one more wire here from neutral to supply voltage O, then I will not get this phi ON. It means there is no voltage difference between neutral point of star connected load and the supply neutral, that is O. If this voltage, this neutral wire from supply neutral to star connected neutral is not connected, so there will be a voltage difference between load to supply. So we need to include this phi ON. Okay. Now according to that, for same, tell me for VBN. Yes,
VB naught plus VON.
V naught plus VON. Yes. Next, VCN. Just tell me. VC naught plus VON. Okay. As already told, if wire is not connected to neutral, supply neutral, so I need to include VON VN. This is okay. Now these equation, from these equations I can write the equation for current flowing through all these phases. Correct. Now I got VAN, VBN, VCN. These are the phases across this VAN. Okay, VBN. Okay, this is VCN. Now I have written the equation for VN, VBN, VCN. Okay, I simply write the equation for IA, IB, IC. Okay, tell me, if this is my IA, this is my IB, this is my IC, tell me. Fast. Am I audible, right? I am audible or not?
Yes, sir, audible.
Yes, tell me the expression for IA, IB, IC. We have VAN, we have impedance, the simple formula IA equals to
VAN by ZA.
VAN by
VAN by ZA.
ZA. IB
VBN by ZB.
VBN by ZB.
ZB.
IC
VCN by ZC.
VCN by ZC.
VCN by ZC. Okay, this is how we are going to solve with applying the Millman's theorem. Okay, we have ZA reciprocal of that is admittance. You have VAN, that is the phase voltages with respect to the supply point A to neutral N. See here, don't be confused. This VAN, this one, okay, this arrow I can shift here also. There is no problem, right? See, I can write like this. VAN. Is there any difference between this VAN and this VAN? Is there any difference between this VAN and this VAN?
No, sir.
No. So, with respect to supply and the neutral, whatever the voltage we are writing, that are the phase voltages. I can simply write the voltage across this ZA. Okay, these are the equation for VAN, VBN, VCN. Then I is VAN by ZA, IB is VBN by ZB, IC is VCN by ZC. Okay, this is one method. The next method will be is comfortable for you with that method. Next method, what I'm going to show is the mesh or loop. Okay, mesh or loop current method. Mesh or loop current method. For this, I'm going to consider the circuit. Okay, same star connected, no neutral connect wire is connected. It means 3-wire star connected load. Okay, here supply, this is okay, here A, B, C, this is ZA, ZB and ZC. Fine. I'm going to mark the potential for this voltage plus minus, for this plus minus. The line voltages, the VAB and VBC, because we need to analyze this 3-wire star connected load with mesh or loop current method. Okay, what usually you do in mesh or loop current method? Anyone, please? What usually will do in mesh or loop current method? Yes. So I will tell this is VAB, means this is there is a supply is there, VAB. This is a voltage source. Okay, this is not open. There is a loop. I am giving hint, so please tell me. Okay, what usually we will do in mesh or loop current method?
So find the current in the closed.
First, we need to mark the loop current. Correct. How many loops are there visible here? Yes. How many loops? we can see in this figure. Two loops. Okay, first loop and second loop. Okay, now I'm going to mark this one as I1, this one as I2. Okay, now current entering into this element, I'm going to mark this as plus, plus, minus. Okay, current I2 is entering B, so plus, minus. Here ZC plus, minus. Okay, now next step, apply KVL to loop 1. Here this is loop 1, this is loop 2. Now apply KVL for loop 1. Yes, apply and tell me for this. Here plus to minus, minus I1 ZA. Next, with the ZC, two currents are related. Correct? Now minus I1 ZA, then we are following this one, right? KVL to
Minus I1 ZC.
minus, see, one
Minus
more
ZC.
current is
Sir,
related.
I understood. ZC of I1 minus I2.
I1 minus I2 ZC. Next, which voltage?
VAB.
Yes, VAB, that is plus or minus.
Minus. Plus, sir, plus.
Plus to minus,
Plus
plus
to plus.
VAB, plus VAB is equals to 0. Okay, if going to simplify this one, I1 ZA minus I1 ZC minus minus plus I2 ZC plus VAB is equals to 0. Okay, now I can get minus I1 ZA plus ZC plus I2 ZC plus VAB is equals to 0. Now I can shift this voltage that side. So okay, equals to minus VAB. Finally, I'll get I1 ZA ZC minus I2 ZC equals to VAB. This is my equation 1. Now same, apply KVL to loop 2. This loop 2. Yeah, tell me. Minus I2 ZB, then minus of I2 1 ZC, then VBC, that is VBC or VAC.
VBC, sir. VBC.
Yes, VBC. Minus I2 ZB minus I2 minus I1 ZC, then minus VBC equals to 0. After simplifying this one, I'll get I2 ZB minus I2 ZC plus I1 ZC minus VBC is equals to 0. Okay, from this I'll get I1 ZC, I1 ZC minus of I2 ZB plus ZC equals to VBC. I'll call this one as equation 2. Okay, now if I'm going to solve this equation 1 and 2, I'll get I1 and I2. Okay, after simplifying these two equation, what I get is, directly I'll write here, I A is equals to I1, then IB is equals to minus I2, then IC is equals to I2 minus I1. After simplifying these two equation, I'll get IA equals to I1, IB equal to minus I2, IC equal to I2 minus I1. Okay, then the phase voltages can be obtained by multiplying the phase voltages by the impedances. We know that, and how we are going to calculate Phi Pbn, then Vcn. We need to calculate phi A to this neutral point, this n, phi An, phi Bn, phi Cn. Okay, I have Ia, Ib, Ic. So simply, if this is my current Ia, Ib, Ic, I can write Ia ZA, Ib ZB, Ic ZC. Okay, these are the two methods we are going to analyze our unbalanced three-phase loads. That may be 3-wire star connected load, that may be 4-wire star connected load. In that, if neutral with zero impedance and neutral with some impedance and delta connected unbalanced load, we are going to analyze those circuit with Millman's theorem or mesh or loop current method. Okay.
Sir,
Yes. Just tell me. Yes, who is that?